All right, the next species we're going to do is this one, HCO3 minus. What's that called, HCO3 minus?
Hydrochlorite. No.
Close, very close, but not.
It's not hydrochloric acid.
No, hydrochloric acid would be HCl.
HCl.
Yeah.
Carbonic acid.
Carbonic acid would be H2CO3.
Oh.
This is HCO3 with one hydrogen and the negative charge. No, it's not hydro. It's not hydro. Hydro. It's not hypo. Hydrogen carbonate. It's the hydrogen carbonate ion, or also known as B. It's also known as bicarbonate or baking soda, baking powder, one of those things. So bicarbonate's very common. Well, we're going to draw the Lewis structure for bicarbonate ion. What do we do? Let's go ahead and do this. Hydrogen has how many valence electrons?
1.
Carbon?
Oh God, 4.
And then we have 3 oxygens. Each oxygen has how many valence electrons?
6.
6. And then we have a charge of -1. So do we add an electron or take an electron away?
Add electron.
Add electron. And so this is 5, and then 3 times 6 is 18. 24 electrons altogether. So a total of 24. Now we have to build the structure for this. And so what should we put in the center of this structure here? C. So we'll put C in. And so what we could do is we could put a C with 3 oxygens like this, and how about 1 H?
Yeah.
Like that. Does that look good? Okay, let's go with that. How many electrons have we used so far?
23. No, not 23, sorry. 1, 2, 3, 4. 2, 4, 6, 8.
8 electrons. So what we do is with the extra electrons, we try to complete the octets to the terminal. And so oxygen's not an octet. Hydrogen's good, right? Hydrogen just needs a duet. And so let's go ahead and complete the octet like this. Like this. You know, we need 3 lone pairs to complete it. And then like this. Okay, now are we at 24 electrons?
We're at 23.
Let's just double check. We had 8 here, and then 10, 12, 14, 16, 18, 20, 22, 24, 26. This is 26 electrons. We don't have 26 electrons, so we can't go to 26 electrons.
Can we just take away any of the...
Well, actually, yeah, let's take away.
Do they have to be linear?
And so, which one would you take away? Maybe one from one and one from another?
Yeah.
If you take one from one and then one from another, is that stable?
No.
What do we call those? You know, where you have this lone electron. We call that a. We saw this yesterday with NO and NO2. What did we call those?
Can we do a double bond on one of the oxygen?
We can try it and see.
Okay.
We'll try it in just a minute. What do we call it when there's a dangling electron like that? Anybody? I mean, did anybody write it down in your notes? Do you have it from yesterday? NO and NO2 were the 2 examples. It was in the PowerPoint slide. NO and NO2 were examples of
Unsatisfied valence, mobilized atom.
Somebody have? None? Yeah, what do we call that? Free radicals. Free radicals. So we try to avoid free radicals if possible, and this is an even number, so it should be possible to avoid free radicals, because are free radicals stable? No, so let's just take it off, both off one oxygen. That way we don't create a free radical. Okay, does this structure look good? Now we have 24 electrons. This is good. Is this good? We do need the brackets, like this, and we do need the negative sign. Okay, now, is it good? No, what's wrong with this one? It doesn't have an octet. Do you see which one doesn't have an octet?
The left.
Yeah, this is lacking an octet. So what should we do? If this one doesn't have an octet, how can we make it have an octet? Because everything else, this has an octet, this has an octet, this has a duet.
Can we give it a double bond?
Can we give it a double bond? Well, the one thing that's possible is we take one of these pairs and make it a bond. So we'll take a lone pair, make it a bonding pair like this. But does that give it an octet? Now do we have an octet? And then what did we just do to carbon?
Make it 10.
Yeah, we just screwed up the octet on carbon. And so we tried to make an octet, but it's the same. We still don't have an octet, and now we screwed up carbon's octet. And so we don't want to screw up carbon's octet, so we'll leave it there. Is there some way we can get an octet on that oxygen on the left? Anyway. Uh-huh. Yeah, there's no way. This structure is no good. No matter how long you sit there and try to think, this won't work. To give you an octet. And so we have to think of a different structure. Well, a different structure might be something like, what we saw yesterday, where we saw a COH. Remember the COH? What was the COH from? COH link. Alcohol, right. And so it might be like a COH type link. And so let's try that instead. So if we do this and make the COH link and then put the oxygens like that, then how many electrons have we used up so far? 8. 2, 4, 6, 8. And then we'll complete the octets to the terminal atoms. So this will need 3 pairs. This will need 3 pairs. So then I'll get 4 pairs. And this will just need 2 pairs here. And so now how many electrons have we used up?
22.
See, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. And so that checks out.
So what happens with the carbon's octet?
Except, yeah, carbon doesn't have an octet. So we're at the same problem here. We don't have an octet on carbon, but we have a solution here. And the solution was, what was the solution? We make a double bond. And so if we've used up all the electrons and the central atom still doesn't have an octet, an easy way to make an octet is to take a pair of electrons off a terminal atom and move them into the bond like this. That way we keep the same number of electrons and we keep the same octet on the oxygen, but now what we've done is we've made an octet on carbon. And so that's what we'll do here. And so I'll just show that as a step. Now, the situation is, which oxygen is going to sacrifice the pair of electrons?
Does it matter?
Well, let's see if it matters or not. Okay. Is it going to be this oxygen? That's choice 1, or this oxygen, 2, or this oxygen, 3. 1, 2, or 3. Either 2 or 3, yeah. 1 is not good. Why is 1 not good? Well, let's take a look. So let's go with option 1 here. If we go with option 1, and then we're going to compare it. So we took this lone pair here and made a double bond here. And we end up with this. Now we need the square brackets and the minus charge here. It's option 1. Okay, that's 1. Let's take a look at option 2. If we did 2, we would end up with this structure here. And if we did option 3, we're going to end up with this structure here. Just write it over here. Okay, does this one have octets? Well, the hydrogen doesn't, because the hydrogen duet, that's good. What about with this oxygen? Does this oxygen have an octet? Yes. Does this carbon have an octet?
Yes.
This oxygen? This oxygen. Oh, it all checks out. How about this one?
Yes.
All octets, right? We're good. And this one? All octet. So, according to the octet, it doesn't matter which one. But there is a difference. The difference has to do with formal charge. This is where formal charges can help us determine the most stable structures. It looks like all 3 are fine, because all 3 have an octet. But when we look at the formal charges, they're different. So let's calculate the formal charges here. What do we do with formal charges? Is it winner take all or 50-50? It's 50-50. So if we split this in half, then hydrogen gets 1, and oxygen gets the other. So hydrogen ends up with 1 electron. How many did it contribute? 1. So its formal charge will be 0. It broke even. So the formal charge here is 0. Okay, let's look at this oxygen. So we got 1 electron here, and then these 2 belong to it. So that's 1, 2, 3. And then we'll split these 4 electrons. These 4 electrons in the double bond, this is called a double bond. 2 of them are going to go to oxygen, 2 of them are going to go to carbon. So that's 1, 2, 3. How many electrons? 5. How many electrons did oxygen contribute to this Lewis structure? 6, and it only got 5 back. So if it gave 6 and only got 5 back, then what charge does it get? -1 or a +1? It comes out positive. The reason it comes out positive is because it's lacking electrons. Electrons are negative charge. So if it's missing an electron, it's going to end up being positive. How about this carbon here? Can you look at it and tell me what the formal charge on that is? Plus 4 is the formal charge, or 4 is the number of electrons it
4
has?
is the number of electrons.
4 is the number of electrons it ends up with in the structure. How many did it contribute to the structure?
4.
4. So it contributed 4 and it ends with 4, then it broke even, which means the formal charge is 0. Zero. Okay, and then these two oxygens, you see they're the same bonding kind of arrangement. 3 lone pairs, 1 single bond. What's the formal charge on each of those?
Plus.
Is it plus? Well, how many electrons does it have, each oxygen?
6.
It has 6. How did you count it? 2, 4, 6. That's it?
No.
What about the bond?
8.
No. 8?
Is it 1?
Do we split it in half, or does winner take all? We split it, and so the bond consists of 2 dots. One of the dots goes to carbon, the other dot goes to oxygen. And so that makes a total of 7. How many did oxygen contribute? 6. So it came out with an extra electron. Extra electron is going to give it a negative charge. Right, and so this is going to be negative, and this is going to be negative. Okay, so what we do is, remember when we're thinking about redox properties, what's the first thing you do? The first thing you do is you look at the oxidation states, or you look at if it's an oxidizer or reducer on the chart, non-metal, metal, this kind of stuff. So the first thing you do with these, when you have multiple Lewis structures that are possible, you look at octet. That's the first thing you do. We eliminated the first structure we drew for this because we couldn't satisfy the octet rule. Then we came up with the second one. Now we have multiple structures here that can obey the octet rule. However, we got to figure out, are these all the same in terms of stability, or is there a difference? And so what we'll do is formal charge analysis. So let's do the same thing here. Tell me the formal charge on this hydrogen. 0. On this oxygen.
2, 4, 6, so 0.
0. Good. This carbon.
1, 2, 3, 4. Yeah. 4, so 0.
0. This oxygen.
2, 4, 6, 0.
0. This oxygen.
Minus 1.
Good. Okay, what we see is this. As far as a fair distribution, which distribution of electrons is fairer? The first structure here or the second structure here? The second is a much fairer distribution of the electrons. Everybody kind of got what they contributed, except one came out extra. One's got to come out extra because this is an anion. So we have an extra electron in there.
Is it bad that they have extra electrons?
No, it's not bad because we can form ionic bonds that way. When we look at this one, think about a tug of war. The difference between this one and this one are these 2 oxygens. These 2 oxygens, if they're in a tug of war for electrons, one oxygen lost, the other oxygen gained. Does that make sense to you? Does that seem like a stable scenario? If there's a tug of war, oxygen versus oxygen, one oxygen wins, the other oxygen loses? No, that doesn't make any sense at all, because oxygen should have the same, roughly the same electronegativity. They should have roughly the same electronegativity, which means they're going to have the same pull for electrons. So this is going to be an unstable situation. So this structure versus this structure is going to be a heck of a lot more stable. And so because of the formal charges here, we're going to rule out this structure. It does not look good, because sometimes we can't help it, but if we can help it, then this is better. Now let's take a look at this structure here.
Would that be the same?
It would be the same. All these are 0. Except for this one. This one is going to be minus. This is going to be 0. And so 2 and 3 should have the exact same energy. The exact same energy. In fact, 2 and 3 are what we call same. They aren't exactly the same because we had 2 choices. Remember, we had the 2 choices here. And so they aren't exactly the same, but they are the same. You know, same energy. And so what we'll say is this. There are 2 possible structures, and these structures we call resonance forms. And so one resonance form is like this. With the negative formal charge on this oxygen. And the other resonance form is like this, where the negative charge and the double bond is moved.
Yeah.
Because the double bonds move down to this oxygen and the negative formal charge is moved to this oxygen here. In fact, we can interconvert between these 2 resonance forms. The way we can interconvert between these 2 resonance forms is like this. If I imagine this lone pair dropping down into the bond here, that's going to give more than an octet to carbon, which is going to kick out this lone pair here. And so if this lone pair moves here into the bond, forms a bonding pair, and this bonding pair moves out here, forming a lone pair, then I switch over to this resonance form. Now once I'm at this resonance form, I can revert back to the other one by taking this lone pair and dropping it into the bond here, and then removing this lone pair and bringing it out here like this. Do you see that? Okay, I didn't draw this right, but it's okay because the perspective doesn't matter. And so these are called resonance forms. Now for bicarbonate, I have 2 resonance forms possible. The number of resonance forms just depends on how many options you have for forming the double bond. Sometimes we have 3 resonance forms, 2 resonance forms. We could have even more than 3 resonance forms. That's possible. And so those are resonance. So let's go through this PowerPoint here. So draw the Lewis diagram for the hydrogen carbonate ion. So they went straight to the correct skeleton, but we didn't because we wanted something more symmetric. And so they have this. Okay, resonance structures and isomers. Well, 2 different things. We shouldn't mix them up because this should be on 2 separate slides. Resonance structures are 2 or more equivalent Lewis structures for a molecule or ion that are created by changing only the position of the electrons, in which the actual species is an average of the resonance structures. Okay, there's a lot said there. 2 things is this. For resonance forms, atoms must stay fixed. Atoms must be in a fixed position. So for example, a lot of people, what they want to do is they want to move the hydrogen. And so what they want to do is they want to move the hydrogen from the left oxygen to the bottom oxygen. So they'll try to do something like this, and they'll call this resonance. And so what they're doing is they're just moving the position of the hydrogen over. No, we can't do that. You know, the atoms have to stay in a fixed position. what we do is we just rearrange the electrons. And so they are created by changing only the positions of the electrons. And so here, only the positions of the electrons. And so we just rearrange electron only. Do not move the atoms. Rearrange electrons. And so normally when we think about resonance, we think about, what do we think about? Have you heard of resonance before? Did I show you the Tacoma Narrows Bridge in Washington?
Yes.
You know? Yeah. Now you have to worry about resonance because certain things vibrate at a certain frequency. You know, the Tacoma Narrows Bridge, there's a certain wind that's forbidden, that energy, but once it hit the loud energy, then it could absorb the energy from the wind and it started swaying back and forth. That's the resonant frequency. The resonant frequency for the hydrogen atom is the red light, the green light, the blue light, and the indigo light on those lines. That's where it resonates. All the others, nothing happens. So we hit that resonant frequency. So what a lot of people think is this. A lot of people think when this is the scenario here, we're just resonating back and forth between this. And so one instant in time it's this structure, the next instant in time it's this structure. It's just resonating back and forth. But what turns out to be the case is the true structure, or the actual structure, is neither this one nor this one. The true structure for this is what we call the hybrid. It's the average of the two. And the way we know that is this. The way we know that is that the charge doesn't flip, you know, back and forth like this. In fact, the two bonds are exactly the same. It's not a double bond. It's not a single bond. The two bonds are exactly the same. And you know what they are? They're called a 1.5 bond. Because it's between a double and a single. So between a double and a single is 1.5. And the charge is not negative and zero. Do you know what the charge is? What's the average? It's 0 and negative. The average would be -1/2. And so the hybrid structure is going to look like this. This is what they're talking about. Resonance hybrid is a species that has an actual structure that is an average of 2 or more Lewis structures. And so the hybrid is going to be the average of those two Lewis structures, the two resonance hybrids. I mean resonance forms here. And so let's take a look at the hybrid structure. The hybrid structure, I think, what we're going to do is this. 2 lone pairs are going to be fixed on each oxygen. The third lone pair floats. So the third lone pair I'm going to draw as kind of a dash thing here. A dash thing here. And then the double bond electrons are going to float between. Actually, they're just going to distribute themselves like this. And so what we end up with is we end up with a 1 and 1/2 bond rather than a double or a single. And this one's going to be a 1 and 1/2 bond as well. And then this is going to have a formal charge of -1/2. This is going to have a charge of -1/2. And so when we sum up the formal charges, -1/2 and -1/2, we get the negative charge like this. The way we visualize this is like this. The electrons are like a cloud, you know, or like a fluid, like a liquid way. So electrons are like a cloud, and what we see is these electrons can move or reposition themselves in this. And so imagine you have a bathtub that's shaped like this. And let's see, in the first structure, we're going to put 2 feet of water and 1 foot of water down here. So this would symbolize the double bond. This would symbolize the single bond. The double bond would have twice as many electrons. We put 2 feet of water here. And then just 1 foot of water here. Is that going to be stable? If you have an L-shaped bathtub, can you put 2 feet on the...
Is this like aerial view?
Yeah, this is a looking down, bird's eye view. You could put, if I put a wall here, then is it possible to put 2 feet of water? Yeah, it's possible. If I put a wall here, then what I'm doing is I'm doing something called localization. I'm going to localize with 2 feet of water up here and 1 foot of water down here, so I'm going to have 2 levels in my bathtub. But what happens is this. The electrons can move. The electrons can move and distribute, then there is no wall here. If there's no wall here, then this is not a stable situation, because if I remove this wall, what am I going to get? I'm not going to get 1 foot and 2 feet. I'm going to get 1.5 and 1.5 feet. And so the other resonance form is like this. The other resonance form, we're going to put 2 feet down here and then 1 foot up here of water. But the reality is, neither of these are the electron clouds is like water, and it's just going to, or fog, it's just going to spread out wherever it can. Because it's trying to minimize the repulsion, and so what we end up with is a hybrid. And so we take those two, and then we get the hybrid, which is going to look like this. It's going to be 1.5 feet and 1.5 feet. That is if there's no wall here. Now, if there's a wall there, then we can't do anything. For example, can we move these electrons around without screwing up things? We can't move these electrons around without screwing up the structure. So these electrons are localized here. These electrons are what we call delocalized, because we can move them around without screwing up the octet or the bonding or whatever else. And so this would be the hybrid structure here. And so that's what they're talking about here, the resonance hybrid. We just imagine the average of that. Okay, so we got, normally when we draw the Lewis structures, we look for potentials for resonance structures or resonance forms, and the resonance hybrid. The resonance hybrid, it takes some practice to draw those. Okay, now this is a different topic, so this should be the next slide. The next slide should be isomers. Isomers, now this is totally different from this. There are no isomers for this. We only have one structure for this, and that was, well, actually two, the resonance hybrid, but essentially it's one because of the resonance form or the resonance structures are kind of the same thing. But sometimes what we have two compounds having the same molecular formula but different structure. Since they have different structure, they're going to have different physical and different chemical properties. Those are isomers. So let's take a look at some isomers. The isomers that we're going to look at are going to have this molecular formula, C2H6O. C2H6O. Sometimes we have more than one central atom. And so for this one, which atom would we draw on the center? Well, we could have O in the center, or we could have carbon in the center. Usually carbon, because it's less electronegative, but you're right, O could be there too, because O likes to form a two-bond. And so let's put one carbon in the center like this, and then we'll bond it like this. And then how many hydrogens do we have? Well, 6, so we'll need one here, one here, one here, one here, one here, and then maybe one here. That takes care of 6 hydrogens. Oh, actually, I got to count the electrons. I forgot to do that. 2 carbons will give us 2 times 4 is 8. 6 hydrogens will give us 6 times 1. And then 1 oxygen will give us 6. There's no charge, it's neutral. And so we don't add or subtract, so we're going to get 8, 14, 20. 20 electrons. How many have we used so far? 8, 10, 14, 16. So let's try to complete the octet to oxygen. 18, 20. Now we're good. Now let's take a look at the structure. This structure, does everything have an octet?
Yeah.
Yeah. The hydrogens have a duet. Are there any formal charges? Non-zero formal charges. Actually, all the formal charges are 0. So this is a good structure. And this is what we call an alcohol. And this is a 2-carbon alcohol. 2-carbon alcohol is ethanol. Ethanol or ethyl alcohol is another name for ethanol or grain alcohol. But if somebody were, let's say you were to purchase this C2H6O from somebody, you have to be careful because you might be thinking that, hey, I'm going to get a bottle of ethanol. But you might not get a bottle of ethanol. You might get this instead. And we have 3 central atoms, carbon, and oxygen. 3 central atoms here. But what we can do is, you see, oxygen likes to be a central atom, likes to do this. And so what we can do is something like this. Let's make a different skeleton and see if that's acceptable too. We'll go carbon, oxygen, carbon. Kind of like water, HOH. And then let's fill in the 6 hydrogens. 1, 2, 3, 4, 5, 6. And then how many electrons have we used? 2, 4, 6, 8 times 2 is 16. That gives us 18 and then 20. All right, does everything have an octet in this structure?
Yes.
Yes. Any formal charges?
There aren't too many.
Yeah. All the formal charges are good. No, being 0 is good. Everything has an octet. So which structure is better? We don't know because both of them look good. Both of these structures look good. And in fact, both are good. Both structures are good. Except this type of linkage, the COC link, is called an ether in organic chemistry. This is an ether. And ethers are, this is called dimethyl ether. Dimethyl ether. You don't want to drink dimethyl ether. You're going to get sick. And so if you were to go out and buy C2H6O, you have to be careful. Which isomer are you getting? Are you getting ethanol, which you might want, or dimethyl ether, which you might not want? It turns out that there are only 2, because if we tried drawing other skeletons for this, those fail. And so there are only 2 isomers. But as the molecules get bigger and bigger, you can have multiple isomers, 3 isomers, 4 isomers, 5 isomers. And so that just takes some trial and error to figure out what all the isomers are. Why are the properties different? Well, ethanol is going to have dramatically different properties than dimethyl ether because of the composition. Well, composition is the same. It's because of the structure. And so structure is so critical for properties that we're going to look at first the shapes of these things, how the shapes differ and this type of stuff. So that's what we're going to do next. In order to analyze the shapes of these things, then there's a certain procedure that we follow here. We do something called the electron pair geometry. The pair is Pair, when we think of a pair, how many are in a pair?
Two.
Two, but this is wrong. So a lot of people call it, instead of pair, they call it electron group geometry because pair is usually associated with two. But in this case, it's not necessarily two. It's the arrangement of electron groups. I'm going to get rid of pairs here. Electron groups around the central atom in a molecule or ion. The reason I'm getting rid of that is because of this. Let's say I have a double bond, a carbon double bonded to an oxygen, something like this. Would you call that two pairs of electrons in this bond here? Is that two pairs of electrons?
That's 4.
Well, actually, let's eliminate those two. Would that be two pairs or one pair? This 4 electrons, so I would call this, I'd call it two pairs of electrons. Would you?
Yeah.
Okay. In electron pair geometry, we call it one pair. And so, does that make sense to you?
No.
No, so let's get rid of the pair and just call it a group. Because what we do is we don't split it up into two separate pairs. We have to take it as a group. You know, they come together. Like say, okay, you know, you're going to get this double bond, but you say, I don't want the double bond. Just give me single, and then you keep the single. You know, it doesn't work like that. It's going to come as one unit, and that one unit will be one double bond. All right, then we have something this. This is valence shell electron pair repulsion theory. And so we have to use pair for this because it's part of the acronym. Do you see the acronym? VESPER. People call this VESPER, valence shell electron pair repulsion theory. And that is the electron pairs. I don't want to call it pairs anymore. I'm going to call it, I'd like to call it VESGER. GER for groups of electrons. Groups of electrons repel each other. And so in valence, electron groups repel each other. They distribute themselves in positions around the central atom that are as far away from one another as possible. And then we have something called the electron group angle. The angle formed by any two electron groups in a molecule or ion in the central atom between them. So this, you know, if we look at carbon dioxide, we have to analyze 3 atoms here. The first atom, oxygen, how many groups of electrons around it? Well, we have what we call a lone pair here. That's one group. We don't split up a lone pair into 2 separate groups. We'll just, this lone pair, that's 2 groups. Now, what do we do with the double bond? Should we split that up into 2 pairs, or should we leave it as one group? We leave it as one group, so there are 3 groups of electrons around oxygen here. Then we go to carbon. How many groups of electrons around carbon? Yeah, 2 groups. Some people will call it 4 because they want to split up the double bonds, but we can't do that. This is 2 groups of electrons. And then around this oxygen over here, we have 3 groups. Now these groups don't like each other because they're all negative. You know, like charges repel each other. And so the groups try to push the other groups as far away from them as possible. And so this is the whole premise of VESPER, or VESGER. It's that the groups don't like each other. And so what we do is we try to separate them as far apart as possible, giving us an angle. We want the biggest angle possible to separate the groups. What's the biggest angle possible with 3 groups? 120. What's the biggest angle possible with 2 groups? 180. And then this is 3 groups, which is 120. And so that's what we call the electron group angle. We talked about tetrahedrons. This is these slides are weird for me. The multiple, but I didn't change it. I should have. change this. But tetrahedron, we talked about tetrahedrons before, but tetrahedron, this is odd because tetrahedron doesn't belong in this slide. So ignore it. So if we represent the groups as sticks like this, these are the group angles. So what we're going to do right now is we're going to do two things. We'll take a break, and then we got to check out our model kit. And so can you check out the model kit from the stock room, and then we'll go on break, or go on break and then check out the model kit.